किसके पास? अरे वाह।
To all the attendees, we will be starting at 3 p.m. Please settle down.
मेरे पास भी रहता है। YouTube पे अपलोड वीडियो है।
One more minute to go live. We'll start in a minute now. A very warm good afternoon to all the attendees from across India who have joined us today. A good evening to all attendees from Asia Pac, and a morning to people from Europe and across the US. Exactly a year ago, Smart Water and Waste World launched the IWET series, the Industrial Water and Effluent Treatment series. The idea behind this exercise was that we believe that there is a huge potential or an untapped potential in the industrial sector, where there are a whole lot of hubs across India where there is a need to do sessions or increase awareness around industrial water and effluent treatment. In the first quarter of 2020, we had done live events in Panipat, we had done Ludhiana, we had done Taloja, where we had close to around, I think, roughly 150 to 200 people in each of these units, in each of these centers who had attended these workshops. The idea was that we create a platform where industrial units in that particular area could come together to learn from experts about the various issues that they face around water and effluent treatment in the industrial sector. Unfortunately, the COVID situation put a kind of a stop to these sessions, and around 2-3 months back, we came back with the industrial water and effluent treatment in an online format. This is the season 1 of the IWET series in an online format. This is the 3rd edition for that, and for the first 2 sessions we have had close to around 900 to 1,000 people who have attended these sessions. Today I come to you live from a city called Miraj, which is on the outskirts of Maharashtra near the Karnataka border. And for the last 3-4 days, I have been having meetings and visiting a whole lot of sugar factories that are there in this belt. And meeting a lot of these sugar factories, I've realized again the tremendous untapped, I would say, potential that exists today. All of the factory managers that I've spoken to over the last 2-3 days continuously tell me how water treatment and maybe then looking at effluent treatment is a big issue for them, and also specifically now with compliances setting in. And I believe that maybe once the COVID situation improves, we can have a hybrid mix of online sessions as well as physical sessions in various hubs across the country. So, taking this session forward, we have 2 more episodes of the IWET series in season 1 on February 22nd and March 22nd. And for today's session, we have an excellent lineup of industry experts who are going to share their knowledge and the various issues that confront you and try to give you solutions to questions that you have. So I would now like to quickly start our session today by having our first speaker come on board. We have Mr. Ajay Popat, President for Ion Exchange, and I would now like to invite him to start his presentation. Before he starts, just a quick request to all the attendees that please put your question answers in the Q&A box instead of in the chat box, because then it's easier for me to take these questions to the relevant speakers. So over to you, Ajay.
Yeah, thank you so much, Mr. Shirodkar. Good afternoon to you. Good afternoon, ladies and gentlemen who are attending this webinar, and also warm welcome to all the speakers in this particular episode of your program. So I will start sharing my screen now, and as you know, and it's in front of you, that the topic that I'm going to speak upon is on integrated waste management process with resource recovery. Two very important points in the title and the subject of my presentation. One is integrating waste management, which is both liquid and solid waste, and very importantly, what the world is looking at from the point of sustainability is resource recovery. So let me present to you this very interesting concept where we can treat raw sewage through a membrane bioreactor. And here, very specifically, I will bring a technology component through introduction of Indian IPC membrane bioreactor. You can combine the raw sewage or the sludge, either the raw sewage or the sludge with kitchen waste, and together it can be treated in a very integrated way in order to produce purified water. So 90% of your resource recovery would be in the form of purified water. You would have a substantial portion of renewable green energy through the biomethanation process integrated in this treatment technology. And whatever is the residual is rich fertilizer. I quantify rich or I qualify rich in terms of the amount of nitrogen and phosphorus content in this residual. So the energy could be heat energy that can be used for industrial application, or it could be electrical energy. And this is how the whole concept is applied. Let me take you through the salient features of each component of the integrated waste management, beginning with the IPC, integrated permeate channel membrane. It's an innovation in MBR technology as it combines the advantage of flat sheet and hollow fiber membrane systems while eliminating the disadvantages of the classical flat sheet MBRs. The disadvantages of the classical flat sheet MBRs are that they were not backwashable, their packing density was less, and their operating flux rate was no different than the hollow fiber or any other MBR that was used. And it put a serious limitation onto otherwise its strength area, whereas compared to hollow fiber, it was much more easy to operate and maintain in a very difficult regime in which it was applied. So it uses a first fully backwashable membrane, which can withstand delta P of more than about 2 bars. So like all MBRs, it's extremely compact, requires significantly lower area compared to conventional MBR because of the high flux rate this membrane systems offer. And of course, like all MBRs, it is available in a modular design. So the key features of this IPC flat sheet is improved fouling resistance. The flux yield is significantly higher than conventional flat sheets. It's almost about 100% more. So if one designs an MBR to treat sewage with a flux rate of about 25 LMH, our experience has been on field that you can easily design the systems at about 45 or 50 LMH. So it is here, it overcomes the disadvantage of flat sheet MBRs compared to hollow fiber due to lower packing density. And you can construct these modules in double decks, you can construct into triple decks, and thereby you can overcome the limitations of the packing density and the area, which is a big advantage when you do a triple deck system design. Robust design because the membrane is made up of advanced PVDF. Conventionally, most of the flat sheets were available on polyether sulfone. So this is one more improvement for flat sheets in terms of material of constructions and the strength of the membranes. Lower aeration demand up to less than 50% when you do a double deck system. When you do a triple deck system, the aeration demand goes down by even 30% of conventional MBRs. So combining all the advantages of PVDF, better fouling control, double the flux rates, triple deck configuration, these systems can be used to treat sewage in an integrated waste management process at a very, very competitive cost. Once the sewage is treated, and if you are going to take the sludge, and that's where we want to treat the sludge coming out of a sewage treatment process, it need not be from an MBR, but in this concept, we have integrated MBR along with treating solid waste. So the sludge which comes out of sewage treatment process, in this case IPC MBR, is then combined together with the organic kitchen waste. So this is segregated organic kitchen waste, and the homogeneous slurry in a pre-treatment is fed to a unique anaerobic digester. So this is a solid digester where the organic solids are degraded through a series of biochemical reactions, which are very common for anaerobic process, beginning with hydrolysis, acidogenesis, acetogenesis, and methanogenesis. The difference here is that this is a solid digester with extremely high organic volume loading rate, and it can tolerate solids right from about 12 to 16%. So this is the unique differentiator in the digester design. And one can produce methane or biogas with the methane concentration of 65 to 70%. And subsequently, the gas can be cleaned in order to go right up to about 90%, or even up to about 99%. And the digester is a rich fertilizer. The biogas generated by treating sewage sludge, or as I said, even sewage, along with the organic kitchen waste, is stored in a biogas storage tank or a balloon. One can use additional moisture traps and H2S scrubbers in order to remove the corrosive H2S in case if the biogas is going to be used for power generation. It is then fed to a genset for electricity generation, like any other anaerobic waste treatment to electricity production. And all the safety which is required in terms of biogas flare, automatic flaring of excess gas is all inbuilt in the design of this system. Integrated with this liquid and solid waste treatment is the odor control system, which is also completely automated, and it captures the foul odor which comes during the transfer of sewage, or the transfer of solid waste, or the transfer of sewage sludge, in case if you want to use sewage sludge along with organic kitchen waste. So the whole environment which is laden with foul odor is then completely insulated from bad smell during the process and during the operations by capturing all the odor into an odor control unit, which works on a simple principle of how we work with biomass, how we with attached growth processes in an activated sludge process or an MBBR. So this media is the one where the biomass is grown, and as you'd see over here, the odor containing air is induced along with water, and it is sprayed over the biomass media, where the complete destruction of the odor causing compound takes place. This is also very widely used to treat VOCs in case of industrial effluent. So the system comes integrated with a ventilator, a scrubber, an air distribution system, a biofilter, and a complete control panel. So like the IPC and like the Indian anaerobic digester, this is also a completely automated system. So this is how the system looks like. This is an actual picture of a very big demonstration plant that is in operation since last 2 years in the city of Hyderabad. And you can see how compact the whole system is. So this is the area where the waste is pre-treated, or it is combined together to form a slurry, the organic kitchen waste along with sewage sludge or even sewage. This is the unit where you can house the MBR, the IPC MBR. Post the pre-treatment, it is fed to the high-rate digester for the biomethanation process. This container, as you could see, houses the balloon which stores biogas, the gas engine, and the scrubber. And this is the site office. And this is the auto control unit placed very close to the pre-treatment unit. And you can imagine how compact, and this is an actual photograph of a very large demonstration plant valued at about 8 crores installed and working since last 2 years. The features of this demonstration plant is it can treat sewage sludge of about 100 liters per P equivalent per day. It can treat kitchen waste equivalent to 300 gram of P equivalent per day. And the sewage sludge out of this amount of treatment is roughly about 2,000 to 6,000 kg per day, or 2 to 6 meter cube per day with 1% consistency. So you don't require to de-water this sludge. And this unit accepts organic kitchen waste of about 900 kgs per day. So 2 to 6 tons of sludge with 1% consistency from the treatment, out of the treatment through IPC MBR, and about 1 ton or 900 kgs per day of kitchen waste. This combination produces 65% biogas, almost equivalent to about 10 Nm cube per hour, converted to gross electrical output of 20 kilowatt per hour, and a digested sludge or fertilizer with about 493 tons per year. These figures are important because while we are recovering resources while treating the waste in an integrated way, this become very important outputs in terms of calculating the payback on such investments. Because at the end, we would also like to address the importance of recovery of investment. And with this sort of recoveries, and for this size of the plant and multiples of this particular plant, the payback of the system easily happens in about 5 to 6 years, depending upon the cost of your electricity, etc. And generally for waste management, we do not look at paybacks because our primary objective is to treat the waste in order to meet the standards laid down by the authority, and in order to have a sustainable practice in our operations in whatever way we do. But still, the technology had to be conscious about the payback, and I'm very happy to say that it gives a very attractive payback on the investments. Some application case studies. So this is an example of a 3-star, a 4-star, or a 5-star hotel. And what we have calculated based upon the number of rooms and the number of people who visit a 3-star, 4-star, or 5-star, the size of IPC MBR, which would be about 20 KLD, and the combined waste to energy plant of about 0.58 KLD. In case of 4-star, the IPC MBR would be a capacity of 50 KLD, and a combined waste to energy plant would be about 1.54 KLD. In case of a 5-star, it would be 150 KLD IPC MBR with a combined waste to energy plant or biomethane plant with a volumetric capacity of about 3.8 MLD. And this is the savings in terms of treated water that can be recovered, as I showed in my first slide. In this integrated waste to resource technology, one recovers 90% of the water. So this is the amount of water, which is recovered by treating almost about 20 KLD. The same thing is shown over here in terms of volume. It is 50 KLD, and here it is 150 KLD. Savings in sludge handling and disposal from STP are the figures which are put over. The resource recoveries and the savings on resource recoveries. Obviously, the first thing is the biogas generation. Apart from the cost of good quality water recovered through this integrated treatment process. So apart from water, there is biogas generation. The values are mentioned here for different capacities in a 3, 4, or a 5-star hotel. And this is the equivalent electricity generation. This is the manure or the sludge generated. So a typical value of the sludge would be, manure would be anywhere between 15 to 16 rupees based upon the nitrogen and the phosphorus content. So it is a very rich fertilizer and has got a much better value than most other organic fertilizers. And of course, there is a saving in terms of disposal cost of solid food waste. So when you apply all these savings to the investment on integrated waste to energy process in the hotel segment, the payback is anywhere between 4 to 6 years. Similar case study is also for residential complexes with 200 flats, 300 flats, or 500 flats, each being occupied by about 5 people, generating in a 200 flats close to about 100 KLD of silage and sewage, liquid waste, and close to about 240 kgs per day of an organic kitchen waste. Similarly, in a 300 flat condominium or residential complex, one would generate about 150 KLD of sewage and silage, and roughly about combined waste to energy plant requirement would be roughly about 4.46 KLDs, and so on for the 500 flat condominium or apartment. So these are the figures in terms of savings, in terms of recovery of water, savings in terms of disposal cost, savings in terms of electricity production, and savings in terms of solid waste discharges. Once again, in the case of hotels, here also the payback comes within about 3 to 6 years. In fact, it's about 1 year lower here because of this. So this is the way one can manage holistically both solid waste and liquid waste, and it provides a payback on the investment. Apart from meeting the goals of sustainability, not only by treating waste but also by recovering resources. So waste is the new goal, and thank you very much for listening to this wonderful concept that we have, put it up now commercially based upon our 2 years demonstration, which of course any one of you who wants to visit, subject to COVID restrictions, can just write to us and we can organize your visit to this unit, which is still operated and maintained by us. Thank you very much.
Thank you, Ajay. Thanks for this presentation. I will take a few questions that the audience have put in while you were presenting. So we have a question from INR. He's saying, what is the difference of footprint for flat sheet and hollow fiber MBR plant?
As I said that one of the limitations of conventional flat sheet was on account of packing density. Okay, so hollow fibers would pack more. So hollow fibers would typically be about 50% smaller as compared to flat sheet. But in IPC, because of the new configuration of the membrane in terms of the chemistry, not only the PVDF MOC, but also the chemistry, we are able to get double the flux. So by having double the flux, to that extent, the size gets reduced. But still, it is slightly more than hollow fiber. But by using a double decker or a triple deck configuration, one can be also very competitive with respect to the footprint. Apart from the lesser energy requirement, and also the longer life of the PVDF membranes. And the most important thing is it's so easy to clean flat sheets as compared to hollow fiber, when both of them are immersed in very difficult environments. So the footprint saving is there because of flux rates and because of the triple deck configuration as compared to hollow fiber.
One more question from Hani Rahmani is, he says the main problem of anaerobic digesters is that the CO2 and CH4 products are still mixed in the reservoir. Do you have any suggestions that the two products can be completely separated so that the CH4 can be fully utilized?
I think I mentioned that, but I was probably fast and I was maybe my point was not registered. So one produces about 65% methane in any biomethanation project in a technology process. So subsequent to that, as I showed you in this demonstration unit and in our integrated technology, we clean the biogas and we go right up to about 90% methane or even 99% methane. So from 65 to 90, what we are eliminating is CO2 and also H2S. Particularly when one has to generate electricity, H2S has to be completely eliminated because otherwise it is corrosive for the gas engine. And when one wants to use it up to 99%, we eliminate almost all of CO2 and almost all of H2S.
One more question from Nilesh Tantar. He's saying whether the bioreactors are also included in those containers which you showed in the picture.
Yes, so that was a integrated picture where I showed you in a container where the IPC MBR was. I showed you a pre-treatment section. I showed you obviously the anaerobic digester. There was also the odor removal unit placed at one end. And there was a completely control unit to control the operations also shown in the office block. And also there was a block where one could store the biogas and also the biogas engine. So it was a picture which was completely integrated with all the process units for the integrated waste management.
Okay, Durgesh Pathak is asking a question: how much COD can be required in this process, and also what would be organic loading for maximum treatment capacity?
Well, there is no restriction with respect to COD when you do anaerobic digestions. As all of us know that when the COD loads are high, even when we do liquid waste treatment, right up to about 130,000, for example, in the places where you visited recently, Kailash, sugar mills and distilleries particularly would have CODs of 130,000, and that's where anaerobic digesters are used. But post that you use aerobic digesters because anaerobic digesters cannot reduce beyond, let's say, in such cases beyond 60,000 or 50,000. In this case, whatever is the COD which comes from the sewage or sludge or the digested sewage or sludge after the IPC treatment, along with organic kitchen waste, can easily be fed. So organic kitchen waste, irrespective of the amount of COD load, can be fed to this digester, and one can get the necessary recovery.
So, Mr. Ashok Gupta is asking, what are the possibilities for farmhouses for this solution where farm waste is also generated?
Yes, this is also a good solution to treat farm waste.
Okay, Hemant, I'll take 2 or 3 more questions. We have some time. Mr. Hemant Desai is asking, energy-wise, what type of a system is this? Is this energy neutral, energy positive, energy negative?
Well, when I talk of payback, it is not only on payback of investment, okay, but it's also payback to the goals of sustainability. Because here, if you look at, if you keep aside the price payback, what are we doing? We are supposed to manage liquid and solid waste. Okay, so we would have a treatment process to do it. Here is an integrated process which produces byproducts which are valuable. So you are recovering water, you are recovering energy, and you are also recovering rich fertilizers. So there is actually no waste which you are giving it back to the environment. So obviously, there is a payback in terms of sustainability to the environment and the world we live in.
So I'll take one final question before I go to the next speaker. Nikunj Patel is asking, what kind of skilled manpower do we need to operate this system?
Well, it's a completely automated system that we have built. The simplest of the system which has been practiced in our country is to put up gobar gas plants. My grandmother used to use cow dung. She used to thatch it on the walls of our house, and then she would use it as a cooking fuel. So my grandmother was a manager. She was managing the house and she was managing the utility. I mean, in the simplest form, that is how simple this technology is. But when you look at integrating it with respect to water recovery through IPC MBR, when you look at combining the liquid and the solid waste, we have automated the system. And also, please understand, we also integrated with an order control system. So this system that we have set it up, which I'm inviting everyone to come and visit in Hyderabad, okay, you could see it's completely automated system. And the picture which I showed had a control room through which all the process operations are captured, monitored, and altered depending upon what the feed conditions are and what is the condition of the reactors. So it's a completely automated system. Right now we are running it with about 9 people. 3 of them are workers because sometimes you have to haul something and to make the place clean because you are still want to see that you want to maintain the hygiene of that place. And the rest of the time it's all skilled workers who run this.
One final question. Amrish Kumar is asking, what will be the per kiloliter cost in this process?
Per kiloliter cost of water?
Water?
Not more than 12 to 14 rupees a meter cube.
Okay. I'll take this question from Ramanand Jha because it might make sense to all. He's asking, to whom should we write in case we want to do a site visit for this particular installation?
Well, you can write to me for the, to make it very simple, Ajay.Popat, ajay.popat @ ionexchange.co.in. And or you can just visit our website. You can register yourself with respect to your interest and your inquiry. But for the moment, you can just write on this, and you can also take down my mobile number. It is 932400244. I mean, I don't do this very usual, but I had to give an answer right now. And the ready answer which came to me in terms of contact details and numbers was my own email ID, which I remember, obviously, and also my mobile number, which of course I won't forget. So you can do this, and I will put you on to the right people, and we could get these things organized.
Thanks Ajay for sharing this presentation and answering the questions from the audience. We still have a few questions there, but I will take this up after our second speaker during the Q&A session. So thank you very much for this presentation.
Thank you, Kailash. Thank you, Smart Water, for giving me this opportunity to present this beautiful concept. And of course, I'll remain present because the rest of the topics are equally interesting, and I'll be there right till 5:30.
Thanks, Ajay. Next speaker for the day is Dr. Somil Mehta. He is the technical leader Southeast Asia for DuPont Water Solutions. Over to you, Dr. Mehta.
Thank you, Kailash ji. Good afternoon, everybody. Thank you for turning up in such good numbers. And I hope today is a very educative day for you. You've just heard a wonderful presentation from Mr. Popat on this innovative technology. And I have something equally interesting to bring you on the reverse osmosis process. Let me share my screen. Okay, so I'm going to present to you today on closed circuit reverse osmosis, or in short, we can call it Ccswro. This is a new company that we have recently acquired. It was a startup company just 5 years ago, and now it is part of DuPont Water Solution umbrella. Let me briefly introduce DuPont Water Solutions here. We are the component provider for RO membranes, NF membranes, ion exchange resins, ultrafiltration membranes, and some of the new additions to our toolbox are MABR, or membrane aerated bioreactor, MBR, which is membrane bioreactor, which Ajay was just talking about, and then we have the Ccswro technology, or closed circuit RO technology. Today we will specifically speak about Ccswro and how it changes the game in the reverse osmosis process. I will be a little provocative today in my agenda, where we want to see why this particular technology we are talking about, how does it change the game, how is it different from conventional RO, and what benefits does it actually bring to the end users like many of you. So let us jump straight into the technology without any further ado. If you look at the technologies we are into around the world, you have seen that there are several innovations that has happened in last decades. Earlier, we used to use a telephone, like as you see on your screen, we had a huge television, which was a cubicle box. And back in maybe 20, 30 years ago, if you remember, there's only one channel, Doordarshan, that used to come our way. And today, where we are at, even some of the existing service providers, which provide you a regular channel, is getting out of the game. And now we have this Amazon Prime or Netflix and these type of revolutions coming in, where users can do whatever they want at their will and at their speed. But when it comes to reverse osmosis technology, are we really still stuck in the conventional way? If you look at the reverse osmosis on one side and the concept of refrigerator on the other side, what if you have a reverse osmosis plant that you just switch on and you never have to worry about it until it is broken? Today, I'm sure you would all agree that we have so many headaches to manage a reverse osmosis plant. Whether we have done a CIP properly, are we really maintaining our recovery properly, are we really monitoring our parameters properly? Is there any fouling tendency in our water, blah, blah, blah. The list can go endless. But what if there is an automation or there is a technology that will do everything on its own? And all you have to do is just switch it on and then monitor the system on a computer panel, The system will automatically adjust. You don't have to do anything. You just have to set the parameters that you wish to have, and then it will operate automatically until its life is over. It does it look like a dream to you? But it is not. Let me assure you. I think the technologies are here today which can help you achieve that. So I'm going to show you how it is done and what are the benefits. What will it bring to you? Eventually, if you're operating the system automatically, you can define what kind of recoveries you want, and the system will bring you that recovery. You're not stuck to the flow parameters in each stage. So one stage you can only take 50% recovery, second stage only 75% or 80%. You're not stuck to those kind of boundaries anymore. You define 90%, 92%, 70%. Of course, you have to be judicious about the overall salt solubility and the thermodynamic limitations. But that what we can show you here is the system limitations can be removed. So now you can reduce the water consumption. If your feed water is very valuable, you can do that. If your waste management is an issue, now you can reduce your wastewater by a significant fraction by achieving a very, very high recovery. The overall process, if you look at the conventional system with the same kind of recovery and this Ccswro system with the same kind of recovery, you will see a dramatic energy reduction. The energy reduction obviously depends on the nature of system in which you're operating. If you are under brackish water, very soft water, the amount of energy saving will be lesser because the pump energy isn't required so much. Whereas if you go to seawater side, the amount of energy saving is tremendous. And what if you have no worries of fouling or limited worries of scaling? You can reduce your cleaning by an order of magnitude, whether it is 2 times, 3 times, 5 times, 10 times, it really depends on your system. And finally, what if everything is controlled by these new digital fancy systems? Everything is at control of your palm on your smartphone. You can see all your trends, you can see all the system parameters, and at the same time, you save a lot of money. Right? These are a lot of different benefits packed into one system. Let's get into the advantages of Ccswro. It is very easy to operate because everything is self-controlled. You just have to put in a programming logic and it will automatically control those parameters as per your wish. You can define to change those parameters and the parameters can be changed. Of course, the deciding power is still in your hands, but the equipment is going to abide by what you say. The system is very reliable. You turn it on with your set parameters, and for maybe a year, maybe 2 years, almost nothing happens. The system keeps on churning the water as per your requirement, while it is controlling its scaling and fouling tendency. There are some routine checkups that you may have to do, but it will reduce those checkups at a much, much lesser frequency. And the system is very efficient. Of course, if your water is very hard to begin with, there's only so much recovery you can take depending on the thermodynamic limitations. But if the water is soft, and if you wish to go to 98% recovery, there are systems that are in operation that operates at 98% recovery, where you take it to almost zero liquid discharge type of setup. And that is also possible. So let's look at how Ccswro can do it. I hope the why is compelling, so I am sure how would be even more interesting for you. This is how a conventional system works, right? You have a conventional two-stage system. You have your feed water from one side, your high pressure pump, it goes through first stage, and the concentrate is fed into the second stage, and then you have a concentrated brine. The system is almost like something welded in stone, right? Once you have designed the system, this is how it will operate under whatever feed you have, under whatever conditions you have. The conventional RO systems are designed with a picture in time. It is not dynamic to amend itself to your changing feed, for example. Everybody knows that our feed water is A today, but tomorrow it can be B. Your conductivity can change, your fouling tendency can change. But once you have invested in a conventional system, you cannot change it. or you cannot change your parameters dramatically without affecting your efficiency. So the pain points of conventional system is you have set recovery in your system, and that set recovery is what you get, right? There is a fouling tendency which is concentrated towards the towards the later part of the system. If you have biofouling, then generally your lead elements of the first stage will foul. If you have, let's say, organic fouling, then it will happen throughout the system. If you have, let's say, some other scaling or some other salt precipitation, it generally happens at the tail end of your system. And this is very, very concentrated in that particular region. So even if you hope that your biofouling is distributed, it will not happen. Even if you hope that your scaling will be distributed throughout the system, that will not happen. So generally, if your water is scaling in nature, your tail end elements will get fouled first. If your water is very high in biofouling tendency, your first elements will get fouled first. And that is what you're stuck with. So there is very limited flexibility in the conventional system of operation. The energy is usually dependent on the high pressure pump. Generally, the high pressure pump, once selected, the system will continually operate at that particular pressure. Of course, with VFDs and depending on the nature of recoveries or flow dynamics you're taking, you can adjust the pump pressure a little bit, but your pump pressure is almost fixed for the operation because it has to push the water even out of the second stage. And finally, the consumables, membrane life, CIP chemicals, anti-scalant dosing, other fouling chemicals, all of this depends on how you define the system. And once you've designed that, it is almost fixed throughout your time. While the conventional system are getting a little modernized, there are some very sophisticated data gathering tools and automation which are being applied to conventional system. It is still not automatic in maintaining its operation, or it is still not as flexible in operation. Let me show you what Ccswro is. Ccswro, as the name suggests, it is closed circuit RO. Basically, the RO operates in a closed loop. This is the most fundamental principal difference between a traditional RO and a Ccswro. The benefits are, depending on how many loops or how many cycles you take, you can define the recovery of system. The recovery of system is not dependent on the number of stages, but it is dependent on the number of cycles that you take for your water. The flux. Under conventional system, you can only have a certain limit of the flux or a certain limit of cross flow of water over your membranes. However, in Ccswro, you can define cross flow on your membranes an order of magnitude which is higher compared to conventional system. And this significantly reduces your fouling and scaling tendency. The flux of the system really depends on the high pressure pump, right? And here, again, you can control the flux of a system which is slightly higher compared to conventional system. Moreover, the system is very, very flexible because you have adaptive controls. You can adapt your recovery on the go. For example, your feed water is changing from seawater into a river water or river water into a seawater. A traditional system cannot adapt to this kind of change. Whereas in a Ccswro, the system will automatically adapt its recovery. Let's say traditional system was operating at 80%, seawater is operating at 50%, it will automatically adapt that recovery so that you get appropriate recovery from your system. High pressure pump usually comes with VFD, right? Any system does. Now, as you're taking the cycles of the system, your initial cycles have a very low TDS water. The water is very soft initially. As you keep on jacking up your recovery, the later cycles will have high salinity and the pump will automatically adjust to the pressure requirement. So here is the theoretical curve. For example, initially your energy requirement is low and later it's high. In a conventional system, you're constantly operating pump at a high pressure. So your energy requirement is much higher. Whereas in a Ccswro, you're gradually increasing the pump pressure. So your energy efficiency is significantly better. In case of some certain scaling tendency, which is the predominant problem. For example, let's say silica is your problem. in traditional system, because your tail end elements are constantly subjected to high silica concentration, there is a very high fouling tendency or scaling tendency on the tail end system. However, in case of Ccro, for initial cycles, the scaling tendency is very low. As the system is reaching more and more concentrated, the scaling tendency increases, it reaches near saturation, but for a temporary moment, you could even cross the thermodynamic saturation while your anti-scalant is working in its induction time. So you can push to, let's say, 500 ppm silica for temporary purpose and take out even further recovery from the system, while the anti-scalant controls the precipitation, and then immediately you have a fresh water coming in with your purge cycle, so it will wash away those scaling tendencies. So there are numerous advantages to Ccswro technology as we are describing compared to conventional RO. Let me briefly show you how it will work in schematic diagrams. So let's say you have a first operational cycle or step one, where your feed water is coming in. In the first cycle, the feed water will pass through the membrane systems. Instead of throwing away the reject, you will recirculate it back along with the feed water. There is a circulation pump that really controls the cross flow. So the pressure requirement here is very, very low, only an order of 1 or 2 bars. And there is a high pressure pumps, which is actually pushing the water through the membrane. Because you have a single stage system, the high pressure pump pressure requirement is also relatively lesser compared to 2-3 stages where you have to push the water all the way through. Your footprint is also much, much smaller, and your efficiency of the membrane is also much, much higher. As the water gets more and more concentrated, the color of the membrane here indicates the salinity across the membrane. So there is a slight polarization from first membrane to the last one, just like conventional system. But as the cycle continues, the later cycles will have much, much darker color compared to initial cycles. And at some point, you hit your trigger where the brine flush valve is opened up. This trigger is defined by you. You define it, whether it is based on recovery, whether it is based on some scaling tendency, fouling tendency, conductivity, whatever. Once that process happens, there is a brief period of time where you have a flush cycle. So the concentrate will be flushed out depending on how you define the cycle, whether entire water is flushed out, partial water is flushed out, it depends on you. And then again, you go in the step one and the process continues. So these are the summarized advantages of Ccswro technology and why it is superior compared to conventional RO. You can push the recovery up to 98%. Now, I know this number looks too high to be true, but trust me, if you have water which is soft enough, and if you have regulation that is requiring you to go to almost zero liquid discharge, you can, let's say, go from almost 1000 or 2000 TDS to all the way 100,000 TDS to get almost 98% recovery. The scaling tendency is very, very well controlled because you have those trigger points defined by yourself, depending on the conductivity or a particular ion electrode you can decide, and you can exactly purge the system when you want it. The biofouling tendency is significantly reduced or even eliminated in some cases because your lead elements are now actually processing the water throughout the cycle. And at some point of time, you have fresh water coming in that will wash away those depositions. You can also have periodic CIPs or CEBs where you have an offline cleaning of the system. The energy consumption of the system is significantly reduced. As I said, it could be up to 35% in case of seawater, where the applied pressure is very high in case of conventional system. Whereas in case of brackish water, the energy recovery will be lower, but it will still be 50 to 20%. The system is very, very flexible. Depending on the change in situation, the process will change, and it is autonomous. Everything is controlled at a click of a button and on your phone, on your smart device. And finally, system can be designed with a very high quality equipments and membranes So if the system is designed with appropriate material of construction, it can last for decades without any issue. Let me quickly get into what are some of the real cases where customer has had benefits. So these are some of our partners who have already a significant footprint of these kind of systems, and they are currently using these systems very, very successfully. Let me get into a few select case studies. I saw somebody in the audience from Coca-Cola. So we have a plant for Coca-Cola in Asia. Their main pain point is reducing footprint. And here you have a Ccswro system with a picture with a very, very small footprint. If you can, I mean, these are 8-inch RO elements, so you can almost extrapolate how big is the plant size. With a very small size of the plant, at the same time, it is achieving almost 91 to 97% recovery, depending on the feed water fluctuations through the time. Okay. Here is another example where the challenge was efficiency. Basically brine reduction and CIP frequency reduction. So this is a pulp and paper company in Arizona. It's called Double Tree Paper Mills. You can see the overall process parameters for a conventional multi-stage or two-stage RO system versus a closed circuit system. So you will see here, let me directly focus on the benefits. So the daily water production is almost double compared to the conventional system. Now you look at the number of membranes, you are operating with 28 membranes. If you had to double your water production, you had to almost go to 56 membranes, right? In theory, have two systems. But here you can do so with much lesser number of RO membranes. The daily waste generation is also significantly lower because now you could increase your recovery from 73% to 88% average recovery. The specific energy is also 5% saved. The anti-scalant consumption significantly reduced. And look at the biofouling tendency and CIP frequency, reduced by 1/6 and 1/3. There are several examples where you can do wonders with this technology. Here is a confidential pharma company based in California. They had a problem where the feed water was significantly varying. And here you can see on your screen the black curve, which is the feed water conductivity. So some days you have as good water as 500 microsiemens, and some days you have as high as 3,500. How do you adjust that? A Ccswro technology, when it is defined, when the trigger point is defined based on the conductivity in your reject stream, the Ccswro will automatically adjust the water recovery depending on when the reject stream hits that particular conductivity. So for example, when you have 500 ppm TDS, and you can almost achieve 95% recovery. Whereas when your feed conductivity is 3,500, the system automatically brings it down to about 78% for a brief period of time, and then it automatically boosts it up again. At the same time, in this particular system, we had also defined another trigger point that system at no point of time should produce more than 95% recovery. This was just to ensure that the system is long-term maintained without any fouling tendency. And by doing so, you can see that there are certain period of time where the conductivity is extremely low, but we still capped the performance to 95%. So this is the benefit of automation and a superior artificial intelligence system. Basically, it works for you depending on your trigger points. Yeah. And finally, maybe a last case study here, where we have this another chemical company which is based at Lion Elastomers, and the objective there is again to reduce the CIP frequency. Here also we have this system in operation for 16 months now, and there has been no CIP till date. It is operating at higher recovery compared to other conventional systems. It is operating with smaller membrane footprint, much more water saving, but also significant CIP saving. So with that said, today, as I said, this is a relatively new technology. It is patent protected. There are more than 140 patents on this technology to very well cover the technology confidentiality. At the same time, we have references which are across the globe with more than 250 systems working very successfully. And 80% of these customers have come back to us with repeat orders because they like the technology so much. There is so much efficiency that they would like to ensure that they continue to leverage this. I would like to thank you for your attention on behalf of Desalinitech and DuPont Water Solutions. I would also like to thank Smart Water for organizing this wonderful session, for educating people at the same time sharing the knowledge. And if you have any questions, please feel free to reach us. I have put in email address here. It is india.dupont-water-solutions@dupont.com. Thank you very much.
Thanks, Dr. Somil. I have a few questions that have come in from the audience. So Vishal Wagolikar is asking, what is the max feed of the TOC/COD range for the CCRO technology for optimum organic fouling control?
Yes. Yes. So see, let me answer this question a little more generic way. A CCRO system is a new process or a new way of operating reverse osmosis system. It is not a magic by itself. So whatever conditions are applying today in terms of theoretical limits to RO system, whether it is a scaling tendency, salt concentration, whether it is fouling tendencies levels, or whether it is organic concentration levels, all of them will still apply to CCRO. But within those limitations, CCRO as an operating process methodology can significantly improve the efficiency of the current systems. So as you know, for conventional systems, defining a ppm for BOD COD is very difficult because it depends on the type and nature of COD and BOD. But depending on if you have any experience with your current system, you can implement the same experience with CCRO.
Okay. One more question from Arun Kumar Agarwal is, he says, is there any limitations for adopting CCRO technology vis-a-vis flow, quantity, temperature, etc.?
Yes. See, when you're using a CCRO technology, just like any RO, if you want to go with CCRO technology, there should be a bottom limitation below which maybe the process is not efficient. For example, if you have a system which is, let's say, 25 meter cube per hour or 50 meter cube per hour, below that, the system may not be very efficient. I think 25 is a good number. Because the system will require certain cycling or certain efficiency in order to operate efficiently for you. Similarly, if your system is too big, for example, if you're operating like 100 MLD, 150 MLD type of plants, maybe for those systems, this technology may not be very efficient because your footprint will eventually become so big and your asset size will become so big that it is better to go with the conventional system. But within those limitations, I think this system is perfect.
Okay. Jyoti Mishra is asking, what are the energy requirements for the CCRO technology?
Yes. So as I mentioned, the energy requirement will be very similar, but 15 to 35% lower compared to the conventional system that you're operating. There is a very good chart which is published in one of the articles in a journal based on different types of recovery and different types of feed water for CCRO. And it's a very nice 3-dimensional color chart that you can refer to. Depending on your application and your TDS conditions, you can identify how much percentage energy saving.
Okay. Nilesh Kantak is asking a question, can we revamp or modify existing RO systems with CCRO technology?
Absolutely, you can. You can revamp or retrofit the existing system into CCRO methodology, or you can build your new system in a CCRO methodology. Both is possible.
Okay. Omendra Yadav is asking, is CCRO technology working in any distillery or working with condensate polishing unit treated water?
Yeah, that's a good question. See, we will have to check our references, whether there is any specific reference on distillery or condensate polishing water. I would assume, see, the water is fairly mild other than organic content. So we have to really check the organic content, the nature of it, the concentration of it, and whether it is suited for Ccswro in terms of its controlling fouling tendency. From TDS side, I am not worried at all. So I think it should be possible, but whether we have exact reference or not, I'll have to check.
Okay, Rajesh Joshi is asking any implementation in any Indian pharmaceutical company?
Not yet. That I can confirm to you. This is still a new process that we are bringing into Indian pharma companies. As you would know, so DuPont acquired this company called Desalitec late last year. So we have had a limited time to integrate yet and bring this technology across the globe. So there is no reference in Indian pharma company yet, but we are hoping it will be soon.
Okay. Chirag Patel is asking a question. What is the cost comparison between Ccswro and conventional RO for the same application?
Okay, by cost, let's divide the cost into two types. One is Capex cost, one is OPEX cost. So your OPEX cost is significantly lower, as I mentioned to you, on several different parameters. The Capex cost will be maybe 10% higher compared to existing system because you will need some more sophisticated controllers and devices. We have done a lot of study in terms of return on investment on a Ccswro for versus conventional system. We understand that depending on the saving which you would like to achieve, whether it is energy saving, CIP saving, etc., the return on investment can be anywhere between as low as 6 months and as high as maybe few years, maybe couple of years, 3-4 years. Generally, if you go for big plants like desal plants, huge ones, maybe there the return on investment is much longer. That's where I mentioned earlier that it will be worth it. Otherwise, generally it is less than 3-4 years.
Okay, Hussain Syed is asking a question. Can this technology be a fit for petrochemical wastewater? And Anamika Mehta is asking, will Ccswro work in the textile industry?
Answer to both is yes, definitely. If you're currently using RO systems, which is well prominently used in both of these industries, Ccswro can only enhance those processes.
Anuj Kumar is asking, how much TDS can this system take up to?
So see, just like any conventional RO theoretical limitations, right? If you look at TDS limitation just for sodium chloride, you can probably go to maybe 100,000, maybe even 120,000, depending on if you use the ultra high pressure RO type of membranes in the system. If you couple it with some kind of NF system for brine recovery, you can further pull out the recoveries from this. But there can be limitation based on a specific salt which could be precipitating out, and we have to look at theoretical limit for that particular salt, and that will be the theoretical limit for Ccswro as well.
Okay. Mr. Gwalani, KP Gwalani is asking, what is the maximum size of the plant that you have ever supplied and how many years back?
That's a good question. See, Ccswro, when it originally initiated as a company in Israel, it was supplying desalination plants, and that was about 7 to 8 years ago. So that is probably the maximum duration that we would have reference for. And desalination plants were fairly big. So I have to check what is the maximum size, but I'm sure it is few MLD, few tens of MLDs.
Lakshay Kumar is asking, how much maximum recovery can we expect in CCSWRO?
Again, CCSWRO or Ccswro, you cannot really differentiate between SW and BW. Generally, when you want higher recovery, even you have a softer water to begin with, you generally use seawater membranes because your concentrate is going to go much higher. So you can go up to 98% recovery, as I mentioned in my presentation. Generally, we have seen 90 to 95% recoveries are very, very common.
Okay. I will take the last question, before we go to the next speaker. Dr. Sandhya Singh is asking, is it suitable to phenolic effluents?
See, again, we have to really look it on case-by-case basis. If the phenolic effluent is tolerated by RO membranes, the component itself, then the system, Ccswro system, will have absolutely no problem operating those kind of membranes. We have to look at the overall footprint. If there is more efficiency to treat this phenolic impurities in the pre-treatment, or allow it in the membrane system and look at what maximum efficiency we can get. So we have to look at the overall system and then decide. But general message is, if currently conventional RO is able to manage it, Ccswro can only improve it further.
Okay. Any installations in India?
Yes,
The question.
we already have about 3 installations in India, and there are a few that are in works. So we hope to escalate that pretty soon.
Okay. Dr. Mehta, we still have a lot of questions, but I'm trying to follow the timelines here. Maybe, once all the presenters finish, I can come back to you with all the questions. And anyways, I will be sharing the questions with both you as well as Mr. Popat. You could directly answer, the questions to whoever are attending in case, I miss out any particular question. So thank you very much, Dr. Mehta, for taking time out and sharing this wonderful presentation with us. Thank you very much.
Thank you very much, Kailash ji. I again appreciate all the people in audience for taking time out, listening very carefully, for your attention and so many questions. Also appreciate Smart Water for giving this opportunity, and my fellow panelists for their camera day. Thank you so much.
Thank you, Dr. Mehta. We will go to our next speaker for today's session, Mr. Sanjeev Srivastav. Sanjeev is going to talk about, common effluent treatment plants and the issues and challenges faced there. And Sanjeev is the founder for Action India Limited. Sanjeev, over to you.
Hello, everyone. Hello, everyone. Good afternoon. And first of all, I would like to wish all Indians and others sitting abroad a very happy Republic Day, which we are going to celebrate tomorrow. So it's my pleasure to talk to you guys and share some views on common effluent treatment plant. And normally I prefer to talk about success stories. So that would be the way I would be talking in this presentation.
Sir, did you get the control, sir? It's already past to you.
No, it says you cannot control Ramkumar's screen. So just 1 second. It's not yet triggering. Okay, you can control Ramkumar's screen now. So, okay, I think it will trigger. Yeah. So why common effluent treatment plant? The very simple answer is because I cannot afford my private jet. Everybody would like to have its own wastewater treatment plant, but there are many reasons why they cannot afford. Some of the reasons are they have very small business. They may be located in an industrial cluster with very small land. Their effluent volumes can be very, very low. And there could be several reasons why they cannot afford a wastewater treatment facility. But the bigger question is, can it be allowed to pollute and send the pollution out? And the very common answer by all the governments, institutions, and authorities would be, no, you cannot do that. So for such sector, planners suggested a common effluent treatment plant, and it was covered under MOEF guidelines issued in 1991. Incidentally, that was the year 1990, I joined a company, Inorganic India Limited, as an engineer. So from 1991, we have these guidelines available that even a small industry cannot pollute, and please try to put some common effluent treatment plants. So what is a CETP? CETP is a concept of treating effluent by means of a collective efforts. We understand an organization like Amul, by collective effort, they collect milk from all the farmers and channelize the milk and its products to all the consumers. On the same concept, CETP has to collect effluent from its various, supplier of effluents, treat it and send it. This concept is very similar to a municipal corporation of a city or town treating sewage for all the industrial houses. We have in our municipalities, houses, colonies, infrastructure buildings, malls, restaurants, they all can give sewage to a municipal corporation, and municipal corporation collectively treats this sewage. But there is a big difference between CETP and sewage treatment plant. In my subsequent presentation, we will try to understand that difference. Increasingly, new industrial development corporations and infrastructure companies who are creating mega private industrial hubs, they are promoting industrial grade waters and treatment of effluent as a common facility, mainly to encourage the investors. So CETP would be a way for new industrial grade water as well as treatment of effluent for the mega industrial hubs, which are private, and would be a good business opportunity for many. What are the objectives of CETP? So let's go one by one. First, it allows small and medium enterprises to focus on their core business. Believe me, nobody's business is to take wastewater treatment, but wastewater is everybody's responsibility. So SME sector understands this responsibility, but if we allow a CETP, that will help them concentrate on their core business and let the effluent be managed by someone else. It also achieves economy of scale in waste treatment because many of its members, as to speak, may not have enough effluent. I very often get inquiries from people. They say, I have 3 meter cube per day effluent or 7 meter cube per day effluent. What do I do with that? The person is showing the responsibility, but there is no economy of scale in managing his waste treatment. Then to solve the problem of space and land, small entrepreneurs, they do not have big facilities, lots of spare land to give. So the CETP can help them. And finally, the fourth one, homogenization of wastewater for heterogeneous industrial cluster. Now, this is very interesting point. And this is where I will remind you my previous slide when I say the concept of CETP is similar to that of municipal corporation, but with big difference. The big difference is the heterogeneity of the industrial cluster. And because in a single cluster, somebody may make pharmaceutical products, somebody may make alcohol, somebody may make some paint, varnish, somebody just make bread, cake, or some cereals. So the kind of wastewater which is coming to a common effluent treatment plant is very heterogeneous in nature. And a common effluent treatment plant will homogenize the same with respect to flow, as well as with respect to inlet water quality, and make it so-called, in wastewater management, we say is more manageable or more biodegradable. If the biodegradability is a challenge for certain industry, there's certain industry, they have very good biodegradability. So overall, this homogenization of wastewater is one very good objective which we achieve in a common or combined effluent treatment plant. Then it also allows you a proper methodology to organize centralized disposal of treated effluent and sludge. Because as in some of my previous lectures I've said, we never manage pollution. We always convert one form of pollution to another form of pollution. For example, a word COD, which is a representation of pollution, is either converted into CO2, which is air pollution, or converted into methane, which is energy, and when methane burned, again CO2, which is the air pollution, or a sludge, which is a pollution for the land. So one type of pollution is always converted to another type of pollution, or maybe a more manageable pollution. So organizing and proper centralized disposal of treated effluent to a river body or a pond or a sea, and also managing sludge and putting it to the right place is one very good objective which is served by CETP. And if we try to maintain all the 5 objectives, actually, we comply to MOEF guidelines. Remember slide 2. The objective of CETP was to comply to the guidelines given by Ministry of Environment and Forest. So let's do a CETP. We want to do it step by step. So what we need, the first and foremost thing for making a CETP successful is a management. The role of the government on board is increasingly being questioned these days, because management is typically done by a local industrial cluster. But nowadays, government is also talking about trying to co-manage the facilities. Money is important. We need funds, we need grants, capital expenses, operating expenses, and a very important one is called revenue, because the CETP has to be sustainable in nature. It cannot survive only on funds and grants. So the revenue is very important. Land is important. Technicalities, a lot of technical things like technology, process, who is the consultant, vendors, trainings, and so on. So many technicalities are involved. After all, it's a technical subject, wastewater management. Incoming piping system, how the effluent will come to you. Outfall system, how the effluent will go back to the river. Sludge disposal area, these are the areas where someone has to put his brain. And finally, a validation authority, who will give consent to operate and how we will be monitoring the performance of the facility. So these are the things which need to be done. What we have done in past, let's just try to run this slide quickly. If you have a look, we have got 174 installations, 2015 count. Okay, out of 171, if we talk about performing in the true sense as per the MOEF guidelines, I can say only GTP at Palsana, a textile industry, that was beating all the parameters of pH, suspended solid, COD, BOD, and TDS. Most of the wastewater CETP plants are failing in an area called total dissolved solids. Some are failing in the area of COD. So COD and TDS are the major default. This data comes from, the next slide comes from GPCB website, sorry, CPCB website. You cannot control Ramkumar's screen. So Ramkumarji, yeah, you please push. Okay.
Sir, are you getting access now?
No, it says you cannot control.
Ram, can you check and see?
Ram, you can click for me. Don't worry.
Ram,
Yeah,
can you hear me?
Yeah, it's okay. It is now controllable. So if we see 2016 data from the website, these number of units have become 193. But I did not really find the authentic information about how many are actually performing well. So I didn't put it on this slide. So what are the legal frameworks involved into doing a CTP? The important environmental law related to CTPs are just mentioned here: Water Prevention and Control Act, Air Pollution and Control Act, Environment Protection Act 1986, as well as environment protection rules, the hazardous waste management, and this is something which I just put. If I do a little bit more Google and also talk to the authorities, there are so many other legal frameworks involved into doing a CTP. What is the role of CPCB? It actually provides guidelines and give consent to operate. They also review and monitor if performance is not in line with consent. What is the role of NGT? A new entity comes as NGT. What happened, in spite of doing all these efforts by MOEF, authorities, and CPCB and PCB, there was a public outcry that several of the CTPs were not performing. So now the NGT, being a technical code, comes in picture to really listen to them. And NGT's role is to issue directives and even has power to give closure notice in case some people are not performing as per the expectation of Central Pollution Control Board or Ministry of Environment and Forest. What are the challenges? To be honest, there are many challenges. Let's forget them and look back at the solutions. So solution one is that one has to have an integrated intake system. What I mean, member of the common effluent treatment plant must commit on quantity, COD, compliance, time, fee to CP, and penalty to a member. That's not enough. How do you do that? So even each and every member, if you look at the table, must commit with respect to COD as well as the biodegradability of his effluent coming to ETP, and depending upon its capacity, maybe more than 50 KLD or less than 50 KLD, and type of industry, for example, whether it is textile company or so and so forth, some rules can be set about what would be coming in. And this is very, very important. The next important thing is the time and the traffic, because everybody cannot put the effluent at the same time. So what we talk about, there has to be some kind of sumps in some room where, depending upon the user from a particular industrial cluster, they will be having set timings when they will be giving effluent to this sump, and this sump will be pumping the effluent to the main common effluent treatment plant. What is the integrated intake system? So for example, in one of the projects, there are 94 sump room with maximum 8 connections. So if you have a look at the picture, these 8 connections also has got some kind of valves, and then it is automated via a flow meter. So these valve opening and closing happens on an automatic method, and therefore one is able to confirm about the quantity and time for a particular user group. So this is something which is important. In the same way, there are auto sampler installed in these kind of sump rooms where the samples are collected. You can see some numbers written in the picture: 1, 2, 3, 4, 5, 6, 7, 8. So at a particular time, who is giving what kind of COD, and whether the effluent is toxic or not, that can be tested. So if the effluent is tested, we will talk about penalty to a member, and depending upon the COD, we will talk about feed COD. The next level is integrated intake system. We will check everything again at the CTP inlet, that whatever has been pumped through the various sumps is actually the same thing which is being received. So in between, there is no one who is trying to put up his own pipe and trying to give some kind of effluent to contaminate what is coming the feed. In simply putting, if we'll find out if there's somebody who is unauthorized access to the piping, which is actually in out of the CTP premises. Well, technology is something, we can always complicate this subject a lot, right? But simply putting it, we don't require a very great technology in a CTP plant. Your partially treated effluent comes from the member units, come straight to the clariflocculator, which is called roughing, then go to equalization tank, primary sedimentation, aeration, secondary clarifier, and that's it. And you put it to effluent to the mega pipeline. And the performance monitoring is done by CPCB on an online portal. The objective is not for me to show you the numbers which is written on the slide. The objective is that nowadays it's all fully transparent. The performance of the plant is monitored by online instrumentation, and the data is put on the Central Pollution Control Board portal. Finally, if the effluent is okay, or even if not okay, then the CPCB will alert, but it has to go to some kind of river. So in Ahmedabad, you can see various places where a lot of CTPs and STPs are put. These CTP and STP are actually pumping water back to the Sabarmati River. Now, how do we design a typically CTP plant? So I will just run through some points. Quantity of wastewater generated, characterization of wastewater is important. Inlet feed water quality is very, very important. Wastewater treatability should be discussed and talked about. It should be low in footprint. Mode of disposal of the treated effluent should be agreed. Disposal of the sludge should be always decided. And we should also look forward towards recycle and reuse of the treated water. And finally, very important one is the process must be designed on a modular and scalable option with a little bit of flexibility available for doing it. And what are the various options which is there in all the books? You have to go to preliminary, primary, secondary, and advanced. Depending upon your budgets, depending upon what is your treated water quality aim, you can go. India is going some good CTPs, 2, 3, I know, they are going into advanced area of COD polishing using tertiary treatment. To conclude my presentation, first and foremost, I'll say that there are many agencies working into it. You know, there are 2 slides I have shown you. One comes from Gazette of India Extraordinary, right, published by some authority. One comes from, you know, the ISW standard of discharge. But there is a mismatch between what is expected and what is to be treated. So my one conclusion is that in this CTP and wastewater management area on a centralized basis, we should have some kind of nodal agency, something like Telephone Regulatory Authority of India, which is a single point responsible person or an authority who manages all the telephone or data operations in India. Similarly, wastewater treatment plant also needs some kind of nodal agency. Secondly, technology is never a problem. You know, a lot of time people say technology is not available. So I can assure you all who are my viewers who are listening to this, technology is never a problem in any of the things. Rajkumarji, can you just click it because you are controlling the screen now? Yeah. So you remember this important slide I've shown you. India launches record-breaking 104 satellites from single rocket. So if there is a will, there is a way. There are teams available in India who can make sure that whatever is expected out of CTPs can be done. And my final words are that team action is ready to help individuals, comply authorities, and state India. Everybody, we are willing to work. Just ask for it. Ram Kumarji, my last slide, please. At your team, my entire young team of a lot of professionals, they are capable to look forward to give you advice on any kind of wastewater management facility. Just get in touch with any of our colleagues. You can look for them at LinkedIn or our LinkedIn pages in our company. Thank you very much.
Thank you, Sanjeev, for this wonderful presentation. So I have a query to you, Sanjeev, as to we know that there have been a lot of CETPs across the country in various hubs. And I mean, honestly, it's not that all of them have succeeded and there have been issues. So where do you see an issue? Is it technology? Is it compliance? Is it discipline? Where is it that there is an issue when it comes to CETPs?
You have given the answer, discipline.
Okay.
So what has been agreed at the time of designing, if you do not give it, no wastewater treatment plant will perform. It is discipline at each and every level. Discipline at first level of appropriating the funds which are available to you. There have been many cases where the funds have not been appropriated properly by people. They have siphoned funds from the grants which were available, right? There are cases going on in India on CTPs. Leave aside that. Then on a technology selection side or engineering side, there have been shortcuts. Something which was not from the manuals and not from the books was agreed. And finally, the word, what you said, discipline. People don't care. The member don't care. They feel they have to give effluent to CTP. So there is no check at the primary. But all the good CTPs which I have visited, if there is a check at what is going to get in, there is a very good treatment plan. And there may be some reason why the COD may be very high. Maybe there's some cluster like WAPI, for example. I know that their COD is not 250, it is around 450, because most of the industry is producing organic chemicals which are very difficult to biodegrade. So they achieve a very good BOD of around 25, but their COD still remains 480.
So Sanjeev, in a situation like in an industrial hub, like I visited an industrial hub in Maharashtra, where you have clusters of different types of industries. I mean, you suddenly have a textile, you have seafood or food and beverages, you had chemicals. So how do we design a system or a CETP that tries to address effluents coming from different sectors, because each need to be treated differently?
Exactly. You must first and foremost, these kind of clusters, they have like, in our buildings, we have societies. So we have, each society has got members, and that then they would constitute a board. So their board must talk to each and every user. What is your commitment with respect to quantity and quality? Because if that commitment is available from quantity and quality, any consultant, it's not necessarily me, can predict what is the expected treated water quality to them. The second thing I said is the traffic. Everybody cannot give it together, so we do some kind of rational thinking. Okay, in the morning shift, there are a lot of industries from textile which is giving the colored water. So that time you allow also some companies which are giving lighter effluent. For example, companies which are making soda ash or making something like this, which has got really tedious kind of impurities, not the COD, not the color. So this kind of thinking and planning is required for a wastewater treatment facility to succeed.
Also, Sanjeev, final question is, I had visited a CETP which was run by a society, and that society had members and elected members and all that. And none of them were technically sound or whatever. So where does an accountability lie in a CETP? Because it's run by a society or an association or something like that. The question comes of accountability.
Yeah, the accountability will come when you come for a revenue board. Like, for example, I use this word revenue, which is very, very important. I know a CETP, naming them is not a good idea, but they generate enough revenue to appoint a CEO and 100 people working under a CEO, including technocrat, lab technician, microbiologist, so on and so forth. And that's why they are successful. They are #1 CETP in India. Still, I will say not performing. They are going toward tertiary because their COD is still not in control as per NGT. But NGT also is a body which is of humans, right? We are all people. So they visited this facility and say, wow, they are doing such a beautiful thing. Even internationally, people are not managing effluent in such a nice manner, the way this organization is making. So let me give them 2 years time to put up a tertiary treatment plant. And they are putting a tertiary treatment plant to bring down the COD to 250. But to answer your questions, 100 people are the professional people working as an employee under the CETP, and the CETP is generating that much of revenue to give salaries to these people. If you think that you want to do something big, you have to do it with a little bit of structure, organization, and good people.
One question we have from Mr. Haribhav Wagmode. He is saying how ammonical nitrogen is treated in CETP. Is it by chemical or biological treatment?
Treatment of ammonical nitrogen in Indian context is fairly very simple. I'm talking, sorry, technical stuff, because most of the time our effluent is at such an elevated temperature that ammonical nitrogen is treated on its own. It just puts some air and it goes in the environment, because you can't really control ammonia into the water at elevated temperatures. Having said that, whatever is the left out ammonia which is available, you have to treat it into a biological treatment facility. And for that, you have to invest more money in terms of the higher sludge age in the aeration system. So ammonical nitrogen is converted into buck's body by developing autotrophs into the system. And that makes a system a little bit more expensive, but you can do that. But treatment of ammonical nitrogen is in Indian context is very, very easy. Second, sorry, one more line I want to add. There could be one industry, they might be giving ammonical nitrogen, but others may not. If everybody is giving ammonical nitrogen, then is a problem. But if only 1 or 2 industries are giving ammonical nitrogen, no problem, because for my bug synthesis, I require nitrogen. So ammonia is a welcome thing. Please give it to us in CETP. We will like to have it. Otherwise, we would have to dose ammonia in CETP to improve the bugs.
Thank you, Sanjeev, for this presentation. I will move on to the next presenter, and then post that we will have all the presenters to whom we can ask questions. So our next presenter for the day is Dr. Pushkar Shukla. He's a scientist with Grasim Industries. So over to you, Dr. Shukla.
Yeah, good afternoon all, and very welcome to the presentation, and thank you Smart Water for allowing us to present here. So today we are having, I'll be speaking on the customized performance chemicals which Grasim is having for wastewater treatment. So if we see, if we go by the definition, wastewater is water that has been already contaminated and is no longer suitable for any further use unless and until we treat it. And treatment is in our purview as human beings. So depending upon what is from where what effluent or what wastewater is generated, there are many methods to do it. For example, for domestic, we have sewage treatment plants. For institutional, they have their own ETPs, and for industrial, obviously captive as well as CETPs. We have just seen how important CETPs are there for our small and medium-sized companies. So on the basis of the water consumption, there are a few sectors which are very much water intensive. If we see, one of them is textiles, another is pulp and paper, then we have paper and rayon grade paper. These industries and metal processing. So these industries are very much water intensive, and if we see that they mostly have their own captive plants. In case of textiles, there are many CETPs. So major focus areas, Grasim has been a manufacturer of PAC for a very long time, but this particular sectors require something more than your conventional systems or conventional chemicals. And on the basis of that, now we have decided that we will be focusing on textile, paper, slaughterhouses, metals, refineries, and distilleries. So to take this further and provide customized solutions, we established a water product development and application development center somewhere in 2016, and we have developed and which got a DSIR recognition. And the main objective of setting this up was to have develop new chemicals and new applications, and also provide a complete solution to the customer and have a value addition to our existing product portfolios as well as to the customer. So it has to be a win-win situation. We have filed a few patents, and also we have strategic tie-ups with DST, NERI, and other eminent institute for our product development. We are also setting up a center for plasticizer applications. So these are some of the glimpses of our state-of-the-art R&D facility, which is located at Vilayat in Bharuch district in Gujarat. So we come to the topic after a brief introduction. I will come to the topic. So wastewater treatment, as we have been discussing even in the previous presentation. And briefly, it is classified into physical chemical treatment and biological treatment. Of the physical chemical treatment, there are several technologies are available. And one of the which we'll be focusing today is coagulation and flocculation. But not the traditional way, the new way, what we call it. So this brings me to my first case study, which is from oily refinery and containing oily wastewater. So if we see the oil which is there, which comes into wastewater, is depending upon the droplet size, it is classified into soluble, emulsified, dispersed, and then free. So if we see, there is a continuous treatment system, the physical treatment system, that is the American Petrochemical separator for separating the oil, which will come at the top, and the suspended matter, which will come at bottom, followed by the tilted plate interceptor, which helps in increasing the globule size and separation of the oil. And then we come to the chemical treatment part, which is mainly for the dispersed oil. And earlier, this particular industry was using nearly 3 to 4 chemicals to achieve the result, so that they can improve the performance of the dissolved air flotation. So prior to dissolved air flotation, where it is separated, the there was a dosage of around 3 to 4 chemicals. But with our new Vital 2810 system and followed by Vital A971, we were able to bring down it to only 2 chemicals, and we were able to achieve a norm which is less than 10 ppm in DAF treated water. So you can see this is the DAF inlet and this is the DAF outlet. And if you see before, the red line represents the result which were coming before, that the COD, DAF outlet COD was always around in the range of 600 to 800. But after implementation of the new chemical treatment system, it is significantly reduced from an average of 622 to 416. Also the TSS, significant reduction, and the BOD. So with this treatment, the customer was able to also achieve the final discharge norm, and this all depended upon his DAF performance. So with this system, they were able to achieve their discharge norms as well as increased performance of the DAF with reduced chemical inventory and costs. The similar treatment system for separation of oily wastewater was also implemented for an edible oil processing industry, where earlier they were using only lime and de-oiling polymer. And if you see the doses, lime was around 6000 ppm and 25 ppm of polymer. From there, it was brought down to only 250 and 3. So this is what a right solution is there, that you can significantly reduce the sludge generation, increase performance, and obviously reduce your load into your subsequent biological systems, which will obviously give you better performance. We have also implemented a similar thing for cutting oil. So this is also emulsified oil, which is coming, and earlier they were using the conventional chemicals alum and lime. With the Vital, they were able to reduce it to 1200 ppm, and there was almost 80 to 90% removal of oil. You can clearly see the difference in the color of supernatant, much clearer. Also, the settling was faster, and obviously, if you see, the sludge generation is significantly less. So lower sludge generation, lower disposal costs, and better performance. This brings us to the next case study. This is for a viscose filament yarn manufacturing unit. And normally in viscose filament yarn, it is yarn dyeing process. So in yarn dyeing process, usually dispersed pigments are used. And in this particular system, what was happening that whenever there was a color changeover from one color to next color, they used to, they will send the residual dye solution straight to the ETP. And this was causing a lot of color in the ETP. So initially the customer requested us to was trying our conventional chemicals, which were not able to give the desired performance. So they invited us and we went there. So we studied their effluent and we thought that this D3 channel, that is 200 meter cube per day stream, is only causing the color. And then when we deep dived into it, we came to know that actual problem is caused because of only 20 meter cube of effluent, which is coming, and it is imparting color to the whole 5000 meter cube stream. So we developed a customized solution for them and also asked them that whether they can separate this 20 meter cube stream and then they can go for treatment. And they agreed to that, and hence they had a battery of clarifiers where this 20 meter cube stream was treated separately and then it was sent to the ETP. So instead of directly sending this dye bath to dye solution to the ETP, they send it first to the battery of clarifiers, and then the treated water was taken to the ETP and the sludge was taken to the TSDF site. These are the actual photographs taken from the plant. And if you can see, there is a significant reduction in color for all the shades as well as mixed effluent that is coming. So you can clearly see nearly 99% color reduction, significant reduction in TOC, that is also related to COD. So they were able to achieve both the norms for color as well as the COD, which was imparted because of these dyes or pigments which were being used. So this brings to the next case study. Again, a textile CETP. My previous speaker has very well explained the need for CETPs. And this particular case, where they were earlier not intending to recycle, but to generate the revenue, now they have decided that they will be recycling a part of their this thing. But the challenges they were facing was high sludge generation because they were using conventional chemicals like lime and ferrous treatment. Whenever you use ferrous sulfate, there is a problem that the DO level drops in your biological system because some DO is consumed by iron, and it also gives you a greenish tint always. And since they were using lime and ferrous, there was an excessive load on RO system which they were trying to implement, because if they have to give it back to the industry, the TDS has to be reduced. And also the chemical preparation which they had to do. So we worked with them for almost 6 months, and several trials we took, and then finally we were able to give them a solution which was VitalCo 1880. And this is a completely liquid product, so no need for preparation and anything. Lime was added just to adjust the pH in case it is on the lower side. And then this is the plant outlet. So if we see, they have a complete system where there is primary treatment, secondary treatment, then the tertiary treatment, and then the same treated water is being sent back to the industry. And we successfully implemented this, and they were able to start the recycling process. And as they say that, so the achievements in this case was that effective COD removals are reduced, chemical doses were reduced by nearly 50%, 37% less sludge generation because of elimination of lime and ferrous, lower rise in TDS because of that, and 15% reduction in overall chemical costs. And as they say that, happy customers, they come back for more. So the second challenge which came was that we want to reduce the color now. The member industries which were taking the water, they said that we also want a lower color water. So from existing treatment, we started working with them again, and we introduced a new chemical, it was Vital 630. And that helped in reducing the color significantly from earlier maybe 40% reduction to nearly 70% reduction. And you can see the difference. Now, obviously this comes at a small cost, and since considering the volume, the increasing cost with this performance was nearly 16% increase in cost, but the performance was significantly better. Again, a CETP, example of a CETP where it is a mixed CETP, but textile and metal processing, both effluents are coming into a common sum, and they are being treated. And the conventional chemicals that were used, lime and ferrous sulfate, and there was a heavy dose of around 1300 and 1500 ppm. And if you see the sludge generation in case of this system and the sludge generation in case of VitalCo 1880 and Vital 630 based treatment system, it was significantly less sludge generation, so a lesser sludge disposal cost, because nowadays sludge disposal cost is also increasing, disposal cost, transport cost, everything, and with a significant reduction in cost also. You can clearly see the difference. The one which I was talking about, that ferrous sulfate gives a greenish tint, this we can see here. Another example, same from the textile industry. This was a very basic plant which was having, the only equipment which they had was that a pump which would pump from collection pit into this distribution channel, and rest everything was being operated under gravity, so no moving parts in the ETP. And they wanted to go for recycling because they were facing water shortage. And earlier, again, they were using the same lime and ferrous treatment. We shifted them to Vital 280, the 630 based treatment system with no moving parts in this clarifier and only a distribution channel for dosing of chemicals. And you can see the results. So this is the inlet and this is the primary outlet. So significant color reduction, significant good amount of COD reduction and very low doses. We have also done similar treatments for pulp and paper industry, where you can see that from conventional, we were able to significantly reduce the sludge from nearly by 50% at a lower dose and better color removal with Vital 2803. Another interesting application which we have developed is that normally algae removal, and there are also industries which are cultivating algae for manufacture of biodiesel. And there is a process in which you have to settle the algae. And this settlement has to be very quick so that the oil can be extracted. And if we see, we developed a customized solution, which was Vital 613, followed by Vital 971. And we could achieve a nearly 99% removal of algal content, which was significantly better than what they were previously using. And one of the key criteria in this particular application is that the chemicals which you are dosing should not be coming with the algae. It should not impart any change in the structure of algae, otherwise oil's removal becomes difficult. So we were able to achieve that, and now it is under evaluation, and shortly we will be having a full-scale trial for this. So to conclude, we have the capability to customize solution based on customer requirement, and we have a state-of-the-art facility, and we are open to collaborations, and also we always have a technical support, and what is best for the customer, that is what we always focus on. So thank you very much. Thank you, Smart Water, for providing this opportunity. Thank you, audience.
Thank you, Dr. Shukla, for this presentation. So I have a question for you that's come from the audience. They are saying, can you tell us what is the chemical composition of Vital?
No, actually it is proprietary.
Okay.
Yeah, it is patented, and it is a proprietary formulations. These are proprietary formulations.
Okay. Anamika Mehta is asking, what is the mechanism for the removal of color and TOC reduction in textile effluent, and is the final discharge non-toxic?
Yes, the final discharge is definitely non-toxic. As far as mechanism is concerned, every dye, if it is reactive or whether it is a pigment, it will depend on the nature of the dye which you are trying to use. Like for example, reactive dyes are highly soluble, whereas pigments, they are not soluble in water, but they are dispersed. So depending upon the nature of the dye, the treatment mechanism changes. Usually what happens is that if the dye is soluble, the chemical will bind to the dye first and make it in the insoluble form so that it becomes settleable. Whereas in case of pigment dyes, which are always in the dispersed form, they are insoluble, but they are in the dispersed form. So what it will do is that first we have to take out the new dispersant, and then we can have the coagulation. So it depends on the nature of dyes.
So a question that I have from two people, Ranvijay Yadav and Deepak, Ranvijay Yadav and is Vital an organic blend or an inorganic blend of compounds?
Vital is actually a hybrid blend. It has organic as well as inorganic components.
Okay. Deepak is asking, Dr. Pushkar, is Vital flammable or non-flammable?
No, it is not flammable. It is 100% safe to use.
Okay, is it Dr. Avinash is asking, this was specifically when you were presenting about the algae part. He's asking, is it useful for lakes and ponds?
Lakes and ponds, no, we have different solutions for municipal and these things. So that is a separate product line. So if additional information is required, yes, that can definitely get in touch with me, and I can definitely share that with you.
Okay, Avinash is asking, can it be used to treat?
वेबिनार में बिजी हूँ, बात कर लो.
He's asking, can it be used to treat leachate or spent acidic effluent?
Yes, it can be. There is a specific product for that. In Vital series only it comes, and yes, that is possible.
Okay, Anamika Mehta is again asking, are these chemicals safe, and specifically if they are releasing in final discharge after treatment?
Yes, because mainly the chemical which will not go with your water, it will mainly be a part of your sludge.
Okay, I have a question to you, Sanjeev from Sofia. She's saying, do the industries in a CETP environment pay to have their effluents treatment, and is the rate based on the quality of the effluent or the quantity?
It's both. It's quality multiplied by quantity, and that which gives you a kilogram of COD per day, and the rate is fixed based on kilogram of COD to be dispensed per day.
Okay, a question that I have for Dr. Mehta from Aziz Ghulam Hussain. The question is, can you give us some comparisons of Capex and OPEX between SWRO and CCRO?
Yes. So thank you for the question. As I was mentioning, for SWRO and CCRO, the operational savings would go as big as about 20 to 30%. And the capex could also be slightly higher, because as we have a high pressure system, we require a separate site conduit for pressure management, and that increases the capex a little bit. So we have to look at the size of the system and then design the system, but it would be slightly higher, of the order of about 10 to 20% or more, depending on the system.
A question for Mr. Ajay is from Mr. Charar. Is there any specific, okay, let me see, the question just moved. Okay, is there any specific BOD or COD ratio we have to maintain? Mr. Popat, during your presentation, you had talked about the system.
I think what I talked about was an integrated waste to resource management. So at the beginning, I said if you have one stream of waste, which is sewage or a sludge, then obviously you have to see that you maintain the BOD-COD ratios, most commonly the ratio of 2:1 or 3:1. Okay, so that is what you maintain. Then you look at the solid waste digester, which would digest the sludge or the sewage along with organic waste. The very fact that it's an anaerobic digester is a biological process. It should be amenable to biodegradation through 1:2 or 1:3 ratios of BOD-COD. I mean, all the norms that are required for a biodegradation process in a biological process are the same. So those needs to be followed.
Mr. Popat, Mr. Nilesh Tantak is asking a question that in a residential setup, does it require a separation of the kitchen waste and the toilet waste?
And, it's a very, I mean, generally we do it, no? I mean, we don't mix it. Okay. I mean, we don't, unless his question is that supposing there is a housing colony, and yes, that housing colony is producing sewage, and the housing colony is also producing kitchen waste, right? Yes. So as I explained in my presentation, there's a pre-treatment section where you combine both this waste in order to homogenize it and then feed it to the anaerobic digestion process. Now, before you do that, there is a step further where you will first treat the sewage and recover water, through the IPC MBR. The sludge from the sewage treatment process can be combined with the segregated organic kitchen waste and put it through a digester. So that's the process.
Okay, we have another question from Amrish Kumar. He was saying, what is the life of the wood medium that is being used?
We haven't changed it for the last 3 years now since the plant is in operation. And I would believe that it should be at least about 5 years. At least 5 years.
Okay, Hemant Desai is asking, will the final sludge being used as fertilizer meet the specifications of heavy metals?
Yes and no. Because
Okay.
it depends on case specifics, because I do not see when you're treating a domestic sewage or a sewage, or if you're treating a domestic waste, the quantum of heavy metals would exceed the norms that are specified by authorities. But we have done analysis in our own plant, which is running, and we don't see any issues of heavy metal in the manure or the rich organic fertilizer that we produce.
Okay, Dr. Mishra is again asking a question, Ajay, is that the membranes that you used in the MBR, are they locally available or imported?
Well, Ion Exchange is the largest producer of membrane, and as you know that we have an integrated membrane manufacturing facility in Goa, one of the best state-of-the-art facilities. So these are made in India membranes.
Okay. A question to you, Dr. Shukla, is that what is the optimal absorption dose for this treatment?
No, I think it is there is some misconception. This is not adsorption-based technology. This is mainly for coagulation, and the dose will always depend upon the pollutant load, the color, and what is the suspended solid levels.
Okay. For Dr. Somil, a question from Ashutosh Singh is, what is the efficiency of a Ccswro?
Yeah, so efficiency of Ccswro is basically as you define the efficiency, if it is based on the energy, if it is based on the recovery, or if it is based on the wastage that we generate. So depending on each of these definitions, the efficiency would differ. In general, when you're operating a conventional RO, the efficiency is significantly lower compared to Ccswro. That is where the comparison should be. So if you would like to compare in the absolute terms, you can say from the recovery perspective, let's say your efficiency is 90% if you're taking 90% recovery. Right? So I would go from that angle. Maybe you should think about total cost of operation at the end of your certain period of operation. That's how your efficiency calculation could be more efficient.
Okay, a question to you, Dr. Somil, again is from Hussain Sayyed. He says you mentioned in the PPT that Ccswro will accept previous levels 2000 to 100,000 ppm. In that case, what is your condensate water percentage and concentrated solid percentage?
Yes. So see, generally in Ccswro, like a conventional RO, you will have a concentrate stream which will go out. And that stream is what is your limiting factor. If your discharge, let's say, is capped at 100,000 ppm, then your discharge stream is at 100,000 ppm. Now, depending on that, your incoming stream can vary to any level, but you will eventually get that particular stream by automated control of the system. So let's say your incoming stream is 50,000, it will take 2x recovery or 50% recovery. If your incoming stream is 10,000 ppm, you can almost go to 10x recovery, right? 90% recovery. So depending on your what is the capping or what is your discharge limitation, your incoming stream can be anything, and your recovery is automatically adjusted to meet that particular discharge stream.
A follow-up question to you, Dr. Somil, from Hussain Mohammed is, he says, can you give me an example for difference between traditional RO and Ccswro with a few numbers, and what is the maximum capacity for Ccswro?
Okay, so I think that's where the most of the presentation was focused, how traditional RO and CCRO are different. Uh, Again, going back to theory, what is a traditional RO? It's a single pass RO system where you have stages, first stage, second stage, third stage, etc. In CCRO, you have a circular system, and in circular system, basically you just have one stage, but your concentrate is recycled back to the feed and it loops in that water. Uh, so if you would like to look at some of the numbers, for example, a two-stage RO system can get you up to 75% recovery. Generally, one stage will get you up to 50%. If you're pushing 55%, if you go to three stage, you can probably get up to 90% or 85, 90, that range, right? In a CCRO, in a single stage, you can define whatever recovery you want. You can take 10% recovery, 20%, and accordingly you design your number of loops or number of cycles that the water is taking. So the system is much more flexible. You can almost have a continuum of your recovery instead of like a stage way of operating.
Okay, a question again, Mahesh is asking to you, Mr. Mehta, is on the energy reduction in seawater / high TDS applications compared to the conventional system. Is your statement still valid, or on conventional SWRO systems which are fitted with energy recovery devices?
Yes, it is still valid because all of the systems in CCRO automatically comes with energy recovery device. So that is a net neutral effect in conventional RO and the staged RO. Conventional RO and CCRO. The reason why CCRO is able to get you even higher energy recovery is, for example, a conventional system operating at seawater with a feed of, let's say, 35,000 ppm or 40,000 ppm, but your high pressure pump is still operating at 60 bar, 62 bar. Whereas in CCRO, in the first cycle, you may require only 35 to 40 bar because your seawater is still very mild at this stage. By the time you go to that 50-60% recovery, the last cycle will require that 50 to 60 bar, 65 bar pressure. So your net average pressure throughout your cycles is lower compared to conventional RO.
Okay, another follow-up question for you from Ruben Villamar is, can we use the same membranes for standard RO and CCRO?
Yes, you can use the same membrane, but see, we have to design the system slightly differently. Normally, so for example, DuPont has Wave software for projecting how a standard system will work. We are coming up with a module for CCRO. There are slightly different fluxes in which you need to operate, and there are slightly different trigger points that you need to control. But otherwise, you can still use fouling resistant, high rejection, those type of membranes in the system.
Okay, one more question we have from Mr. Bangane. He's saying, is there any anti-scalant being used for this CCRO system? If yes, how is it modeled given that there is recirculation of brine being mixed with the feed water?
Yes. So see, anti-scalant will be used, or it depends to not use it. You can avoid it. It is a choice. The effect of anti-scalant on CCRO is also similar. If your traditional RO without anti-scalant is operating at lower recovery, with anti-scalant you can go much higher. Similarly for CCRO, the way you will project CCRO for anti-scalant dosage is you will have to work with certain anti-scalant provider, understand their induction times, and understand how much they're willing to support, and then implement the same in CCRO system. So we have this mechanism already worked out with few providers across the globe. So we have options across the globe, and that way we can make some modeling or simulation to support individual projections.
A question to Mr. Ajay from Jackie Cheong. She's asking, do we need to have a certain concentration for raw sewage in terms of TSS? Ajay, a question for you.
Yeah. I heard that. So I was trying to unmute myself. When you talk of treating sewage, I think it's the simplest thing to do. Because I very often say that whether if you eat a hamburger or you eat a paratha, the next day the output is the same. So we are very fortunate that there is tremendous amount of consistency in terms of the quality when it comes to sewage treatment. So there are not too many challenges with respect to TSS if it's a pure sewage. I mean, there are no challenges or no issues because in a treatment process, in a conventional treatment process, you would use a primary clarifier to remove suspended solids, and then you would do the biological treatment. So as in the case of this integrated waste management process, that in case if there is excess suspended solids, you would try to remove it in a primary clarifier. But here we are talking of a variant of an activated sludge process through membrane bioreactor, which itself is a very effective clarifier cum filter so there is not anything specific that you need to do with sewage treatment. There is nothing extraordinary thing that you need to do with the integrated NBR process also.
I know we are going a little beyond time, but since we have close to 400 people still, listening, I think it's fair we take as many questions as possible. So Thakur Prasad Ajay is asking a question. Do you have any specific module with specified technologies for treatment of hospital wastewater and hazardous category? Ajay, that question is for you.
Yes, can you please, I lost you somewhere, Kailash.
So Thakur Prasad is asking, do you have any specific module with specified technologies for treatment of hospital wastewater or infectious hazardous water?
Yes, the answer is yes. We have modular systems to treat hospital water and also hospital wastewater.
Okay. One more question for you from Anish Manam is, do you upgrade the methane in anaerobic digesters by removing the CO2 before the electricity production?
Yes, I answered this question also during my presentation and in the earlier Q&A, but I'll answer it once again, that we provide systems to scrub the biogas to cleanse it of carbon dioxide, H2S, and other corrosive components.
Dharmendra Kumar Ajay is asking you, how much biogas can be generated in 1 kg BOD?
I knew at some point of time I would have no answer. It's nothing to do with the time of the day, but it's a good question and I'm happy that someone asked. So I'll give some thumb rules saying that if you got about 100 tons per day of bio waste, and that 100 tons per day includes the sludge which comes after treating sewage through NBR or any process, or the organic kitchen waste, you'd produce something like about 1 megawatt electricity. Okay, you can have something more in terms of, this is just a thumb rule that I'm giving. So it answers the underlying questions with respect to BOD, because as I said, it does not make a difference when you're talking of treating sludge, which is coming after sewage treatment, combined along with an organic kitchen waste, because ultimately both are organic. And if you take 1 ton of it, you would produce about 1 megawatt net electricity. Net electricity.
Okay. A question to Dr. Somil from Shripad Patil. He says, in your presentation, you have talked about a 98% recovery. What is the basis for this claim?
Yes, so see, basically, I knew that 98% will arouse a lot of eyebrows. See, the basis is still remains the same. It is the standard definition of recovery. But we really have to see what is the feed TDS that we are starting with and what is the concentrate TDS that we are ending up with. It's a volumetric recovery calculation, basically. The benefit of Ccswro is that a single stage can get you more than 90-95% recovery. I think that is more important than the absolute number.
Okay. Again, a question to you from Anuj Kumar. Dr. Somil, is the maximum area required for Ccswro if it is 2000 meters per day with TDS 2500 ppm?
Okay, I think this goes in details of the GI drawing and all the PNIDs. We'll have to take it up separately because we'll have to run some calculations on this and entire system design. Then only we can make those predictions.
Okay. A question to Dr. Shukla from Nikunj. He's saying, is Vital available commercially? And two, if your team can come and do some treatment analysis within their plant?
Yes, definitely. Vital is 100% commercialized, and we do visit plants, not at present because of the COVID situation, but definitely even if they share the details, we'll be able to give some recommendations on the basis of that, and samples can also be dispatched. Definitely, yeah.
There's this repeated question coming. I don't know which panel member to take this through, but anybody could answer. Mohammad Hamza is asking, how can I clean carbon from zinc dust sludge? Maybe Sanjeev, if you want to take this question up.
Yes, I could see it on the chat box also. Are we talking about soluble carbon or particulate matters? So that's the first thing which comes to my mind, because we have many methodologies of dealing with such kind of waste. But if it is a solid powder carbon or powder zinc, then I don't have the answer. But if he's talking about metal which is in soluble form, we can separate it out and rest remains carbon. If I can answer this, because if it is solid form, it's not my subject. I do not know how to remove carbon and zinc. So if he's still listening, he can type in the chat box whether it is in the soluble form or in the solid form.
I'll see if he is. He's typed it soluble.
Yeah, if it is soluble zinc, no problem. Like we can remove zinc by precipitation and everything else remains as carbon.
Okay, a question to Ajay from Devdeep Roy. He's saying, what is the ideal biogas recovery percentage in a winter season as it tends to dissolve more in water?
Well, by the very definition of the anaerobic process, which has temperature as one of its big influencing performance parameter, we generally have the mesophilic conditions to optimize the biogas recovery at a temperature of 38 to 42 degrees centigrade. So we have built huge plants overseas where the temperatures go sub-zero, and we have built huge plants also in India where the temperatures exceed 45 degrees centigrade. So in both these cases, we ensure that the feed to the mesophilic reactor is maintained between 38 and 42 by having heat exchangers and by having temperature control to maximize, and very importantly, to have uniform anaerobic digestion and production of biogas.
A question to Somil is from Sheetal Urane. What is the typical life of these membranes?
Yes, so typical life of these membranes, that's actually a very good point and very good question. See, normally the life of membrane deteriorates because of implementation of harsh chemicals during CIP process. If you operate the plant very well, and if you don't have fouling or scaling, generally CIP chemicals is what decides the life of the system, right? You would throw away these membranes only when it doesn't give you the desired rejection, or it doesn't give you the desired flow because of increased differential pressure and fouling of the system. Normally with Ccswro system, because you're operating in an automated system with a very well controlled trigger points, as long as you have defined your trigger points very well, and the system is under equilibrium in a way, the membranes are going to last for a really long time. You would see at least 1 year or so increment in membrane life compared to your standard system.
So one more question as a follow-up to that from Hussain Mehmed is, can we clean Ccswro or just change membranes?
No, you can clean. Of course, there will be a regular cleaning that would be required. I shared some of the case studies where the cleaning frequency could be reduced by a factor of order of magnitude. We are not talking about 10%, 20% reduction. We are saying maybe reduction by 2 folds, by 4 folds. In one case, we had 6-fold reduction. So you would clean only once, whereas conventional system would be cleaned 6 times. But that one cleaning is still required to rejuvenate your membranes, because over a period of time, it is still an RO membrane, right? And when you're passing your concentrated liquid over it again and again, you will see some deposition. So cleaning with CIP can rejuvenate the membranes again.
Okay, Dhruvi Vyas is asking you as you were speaking that in Ccswro rejects recirculation, will it increase fouling as we recirculate foulants again and again?
That's a very, very good point. See, we have to see what is the nature of the foulant. If the nature of the foulant is scaling type, where you can keep those scale nuclei particles in dispersed form in the bulk liquid, then you can continue operating until there is a deposition on the membrane. But if the precipitation type is, let's say, some polymeric organic content, which is going to permanently foul the membrane, then you have to be very careful. And there, the number of cycles that can be achieved is not much. So we have to really make that judicious decision.
Okay, I will take a question. This is for Dr. Shukla from, he's not given his name. He's saying whether these different industrial effluent purification processes can be adapted for different countries where the issue of water treatment is very topical.
Yes. We are already exporting some of them, and the results are the same what we are getting here. So the effect of temperature or the pollutant load is not much. The system is robust enough. The chemicals are robust enough to handle all kinds of this thing, and even at lower or higher temperatures, we are able to do it. Not a problem.
So a question to Sanjeev from Anamika Mehta. She's saying what type of water treatment technologies are used in CETPs?
You use very simple technology. One is headworks, then preliminary, then primary, then secondary, and then tertiary. That's a major classification. But after that, the decision depends upon, like in biological stuff, whether you go activated sludge or MBR or MBBR or anaerobic plus aerobic combination. So it's all is the characteristics of a typical CETP. For example, if you're talking about a textile park, your thinking will be different. You will talk about a food park, your thinking will be going towards anaerobic and trying to recover some energy out of it. And if you are having a very, very bad effluent like the Dahej industrial area, Vapi industrial area with a lot of, organics pollution with very low biodegradability, your thinking will go towards advanced oxidation technique like Fenton catalytic reactor, ozonation, combination of various things. So your question is very good, but giving an answer on technologies, my final answer would be technology is never a limitation for a wastewater engineer. We have enough technologies in a simple book called MECF and AD, and any of the technology can be adapted there for a typical wastewater treatment facility.
A follow-up question for you, Sanjeev from Mohammed Ali. He says, which type of chemicals are used for wastewater treatments in CETPs?
Usually, CETPs do not prefer to use many chemical, but some CETPs would use the proprietary products as suggested by Dr. Pushkar or color removals, because that's a very, very good idea. It's not only the color that you remove, you also convert a soluble COD to a particulate COD, which otherwise I would have spent money. So on behalf of Dr. Pushkar, I can say his kind of products are quite innovation because they are converting a soluble COD, which is a pollution for me, into a particulate COD by some mechanism, and thereby saving my energy in aeration tanks. So use these chemicals. Otherwise, you use a little bit of polycrolite in the pre-treatment areas. And if you are having tertiary treatment that many are not having, then you will use things like peroxide or ozones.
Dr. Somil, a question to you from Raj Shekhar. He says, suppose we design Ccswro for TDS of 3500 with total hardness of 1800 ppm, but the TDS falls down to 1500. Will the design still work?
Yes, of course. As I was saying, we can even design the system for seawater. And when it falls down to brackish water, in certain cases where the delta regions are involved, you can have certain seasons in which the TDS become as low as 10,000, 1,000. And in the other time, it is as high as 30, 40,000. The system is still flexible enough to automatically adjust these varying feed water conditions. And not only seasonal, the system can adjust even daily if required.
I'll take one final question.
Please call Nidhi Jain. Please call Nidhi Jain.
For Pushkar. So Uday Kumar is asking you, Pushkar, ki, are you also manufacturing color remover chemicals?
These vitals are all manufactured by Grasin.
Okay.
So yes, we are manufacturing that. Yeah, at our own facilities.
There are still a few questions left, but I'm way beyond time, close to half an hour, beyond the scheduled time. What we will be doing is we will be sharing these questions and these chats with our speakers, and they could then come back to any of the people whose questions were unanswered. So I think we have had a wonderful 2.5 hours discussion. Where I've tried to take as many questions as possible. So one, I would first like to thank each of our panel members and presenters for taking time out of their busy schedules and, spending close to 2.5, 3 hours and trying to, answer all of these questions patiently. But a special thanks to all of our attendees, because without them, these kind of platforms would not work. It's finally your questions and your participations that make these kind of sessions very lively and relevant to everybody. So I would like to have a special thanks to all the attendees. Two quick announcements. One, we would like you to register for our next IWET session, which is scheduled for February 22nd. Like I said, we have two more editions to go for season 1. We might take a small break before coming back with season 2. So one, we would definitely like to see you back for the remaining 2 editions. And again, I would like to wish all our panel members and the attendees a very happy Republic Day. And with that, I would like to bring this session to a close. Thank you all.
Thank you. Thank you.
Thank you very much.
Thanks.
Thank you. Thank you very much.